that I'm hoping to explain by making it concrete. So the scenario is in distributed computing, and about 20 years ago, Peter Deutsch identified a collection of what he called fallacies of distributed computing, the things that we try to forget about when we write distributed programs as much as we can, and write programs as if they were not distributed. And there's an assortment of these things that make distributed computing difficult. And the one I'm going to be looking at in particular is this idea of latency. So one of Deutsch's fallacies is that latency is zero, that you can interact with a system, a distributed system, as if the latency were zero. And of course this is not true. This is one of the fallacies. You have to take latency into account when you are building a distributed system. So there are many distributed system frameworks that try to address this latency issue by some kind of batching of requests. So the problem is, rather than sending a request and getting a response back and then sending another request and then getting a response back to that, each of those takes a round trip, and the latency is significant on a distributed system, and so you can't afford to wait for the first response to come back before you send the second request. That takes too long. So the idea with batching is to avoid that problem by sending several requests all at once, a batch of requests into the cloud, and then you get back a batch of results. And in order to match up the responses here with the requests, in order to match up the responses with the requests, they can't just be an unordered collection of things, they have to be sequences of things. But the fact that you're sending all the requests before you get any of the responses means you're not really worried about the order of these, they're just ordered in order to match up requests with responses. So I send a collection of requests across the wire, and I get a collection of responses back, and I match up the responses with the requests, and I only have to incur one network round trip in order to do that, rather than one per request. So this time last year in Vancouver, Andy Gill and co-authors had a nice paper about doing this batching for distributed computation in Haskell. They called it the remote monad pattern. And this is Andy's example. And I'm going to, the point of my paper and the point of the talk is that I think there's a simpler way of doing it than was encoded in Andy's paper. It's a very nice example, a very nice problem, but there's some simple categorical machinery that gives you for free some of what they were building by hand. So this is the Andy Gill's problem. You're interacting with the remote system. In this case, they concretely had an internet-connected toaster, an Internet of Things toaster, and I'm not quite sure why latency is so important when interacting with a toaster, but maybe you're in a hurry for breakfast in the morning, and you don't want to wait for all those network round trips when you're trying to toast. So this is a smart toaster, and as well as being able to toast things, it has an interface that offers three methods. The say method, the toast method, and the sense method. So as you can tell it to toast for a certain number of milliseconds, or you can, it's got a little LCD display on it, and you can send it a message, and then that message will pop up on the display, so you can program it to say good morning, and this text will pop up on the display. And you can also send it a message to get a response back. So you can say, what temperature are you? You can send the sense message to the toaster, and it gives you back a number saying how warm it is. So an interface with which you can interact with this toaster. And I'll have a data type there of names for these commands as well. I'm going to be doing distributed computation with this toaster, so I'm going to be doing remote method invocations, remote procedure calls, if you like. So I'm going to have to somehow serialize my requests and send them across the wire and get responses back. Now, for the purposes of simplicity, let's just say we're sending strings across the wire. You probably want something a bit more basic than that for sending stuff across the wire. So I'm going to suppose that the commands that I want to send to my toaster are things that may be turned into strings. So there's a function called show that takes a command and turns it into a string. which I can send across the wire. And then on the toaster side, some string comes in, and the toaster needs to work out what to do. So the toaster needs to take this string and be able to work out whether it's been told to say something or whether it's been told to toast something. So there's a function for the toaster that will take a string and give you the name of the command that popped up on the other side, and what's left of the string, having parsed that command off the beginning of it. So in particular, I'm not going to suppose that my toaster is a sophisticated system with a Haskell runtime on it and everything. I'm expecting that there's some very low-level code on the toaster, and as a client interacting with it, I can write Haskell programs, but something low-level will be happening on the toaster. So I'm not supposing that my toaster can deal with the GADTs that are in the command data type here. It can only deal with flat data like strings. So my toaster does some stuff, and it gives me back a response. And then back on the client side, if I know the command that was sent, a command that was expecting a result of type R, and I've got a string of response back from the toaster, I can put those together and extract a value of type R from the string, and that's the result of executing the command. So you'll note that the say command is of type command unit. The response you get back from saying is just the unit type. The response you get back from toasting is just the unit type. But the response you get back from sensing is an integer. So if I do read reply, having sent an integer, a sense command across the wire, I expect it to be able to read an integer out of the string that comes back. So now on the toaster side, you have to implement some logic that will do these things. Now, I'm not going to do any clever embedded logic, so think of this as specifications for what happens on the toaster. And what's my favorite specification language? Well, it's Haskell, of course. So these are Haskell specifications of the toaster's behavior. But the point here is that no fancy type stuff should be going on in the toaster. It's basic things that happen on the toaster. So the toaster knows how to say something, and there's a function called exec_say that says what the toaster should do when it says, when it's been told to say something. The toaster should know how to toast something, and the toaster should know how to sense. So there's functions there to exec and to exec_say, to exec_toast, and to exec_sense. It doesn't matter what they do. The point of this is about the distributed interaction, so it doesn't matter what the behavior on the toaster is. And if I have implementations of those methods, then I can put them together to make an event handler on the toaster that reads a string, works out whether it was told to say or to toast or to sense, dispatches accordingly, does something, gets a string as the response of that, and sends the string back. So that's what the toaster should be doing. So this lets me interact command by command with the toaster, and I'm subject to latency delays, and I'm in a hurry for my breakfast, so I want to remove those the latency delays. So this is where the batching comes in. So what is batching? In a sense, what I want to do with batched requests is to make up a little program and serialize the whole program and send that across the wire. And then the toaster interacts with this program, executes the program or interprets the program, and gets some collection of responses and sends those responses back all in one go. And how do we represent programs syntactically so that we can serialize them? Well, the obvious technique is to use free monads. This is what free monads are for. They're the syntactic representation of programs. So if you have a functor that represents the signature of individual commands, the free monad for that functor is programs made out of those commands. And you don't need to think about the structure of the program. The syntax, the signature of the commands says all there is to be said. So if M is a functor, so this is the monad type. For effect, I've given a different syntax than the usual Haskell one, but it's an equivalent syntax. And here's free M is a free monad. We saw free monads, if you were here for ICFP yesterday, saw them in Mathieu's talk, among others. So think of these free monads as trees. A value of the type free monad, free M of F, is either, with some labels of type A, is either just a label, which I've called var for variables, or it's a branching structure, an F-shaped branching structure of children, each of which is more programs. And the third declaration there says if f is a functor, then 3m of f is a monad, and this is the construction of monads. So this is doesn't really matter what the definition is here, but the point is, if from a signature that's a functor, you can build a monad structure. So in particular, if the f structure is just pairs, simpler than our command structure, it's just pairs, then you either have a label or you have a pair of children, and the free monad on pair is a type of binary trees. So binary trees where the branch nodes have a pair of children and the leaves just have a value in them. So the problem now we face is that command can't be made into a functor. It has the right kind to be a functor, but because it's a GADT, it's not sufficiently polymorphic in the parameter type. The parameter type is an index, not a parameter. So you can't make command an instance of functor. If you've got a command R and a way to turn R's into S's, there's no mechanism to get a command S. So there's a trick which it was pointed out to me is called the co-Yonede trick. It's related to the dual of the Yonede lemma. But anyway, the idea is that I can pair a command R with a function from R's to A's, and those together in some sense represent a functorial thing in A. And in particular, if I know how to turn A's into B's, I can turn an action A into an action B just by composing the functions. And now that is the kind of thing I can make into a functor. And so the data type there, action, is indeed a functor. And then I can use that as the machinery for a free monad. It's a functor, so I can get a monad out of it. So the free monad on the functor action is a data type of programs. So these are going to be my programs. So now I can write some programs. So I can write individual atomic programs, a single instruction program for each of my commands. So I can have a program called say, which just does the say action, and whatever it gets back, that's the result. There's a toast program that does the toast command, and then whatever it gets back, that's the result. And there's the sense program, which is just the sense command, and whatever that gets back, that's the result. So individual statements. But I can also compose them because this is a free monad, it's a monad. I can use do notation to write programs in terms of these free monads. So I can write composite programs. For example, a straight line program that says hello on the toaster, toast for probably 3 milliseconds is not going to do very much to your toast in the morning, but you're in a hurry. And then say goodbye again. So a straight line program. I can also write branching programs. So I send the toaster the sense command, I get back a temperature, call it T, and then depending on T, so if it's not warm enough yet, I toast for a bit longer, and otherwise I tell the toaster to say, now I'm hot. So I can write programs in terms of these things. So can I send these programs across the wire? Actually, no. It's rather difficult to serialize these free monad things because they're infinitely branching. In effect, a sense node in my program gets back a t, which is an integer, and so it's and depending on that t, you can get various different programs that you follow with, and so it's a very wide tree node. It's a tree node with a child for every possible integer, and there are an awful lot of integers. So you can't serialize one of those programs. You'd have to serialize the function somehow. So you might say, let's not do that. Let's make only finitely branching things. So I might restrict my actions to be only finitely branching functors. So this is action F for finitely branching actions. And if the R type, the type of results that my command is supposed to retrieve, are bounded and enumerable, then I can enumerate the branches. So I can just count up from min bound up to max bound, and I can make a tree out of that. So now we can serialize programs and we can distribute them across the wire. But this isn't a very good plan, because although those trees are enumerable, they might still be quite wide. It might not be integer, it might be int. That is bounded and enumerable, but you certainly don't want to enumerate all 2 to the power 32 different children and send that across the wire to your toaster. You really will be late for work if you do it that way. And this is because monads are the wrong tool. Monads allow a subsequent command to depend on the result of an earlier command, and that's exactly what we don't want to do when we're batching requests across the wire. We want to send a collection of independent requests across the wire. The second request should not be depending on the result of the first request. The whole point is that we're going to send the requests off in a batch, so we need to decide the second request before we've seen the result of the first request. We don't want monads, we want applicative functors. And that's the lesson, that's the idea. Free monads are the kind of go-to tool for representing the syntax of programs, but in this case, that's too general, and what we need is applicative functors, which are the go-to tool for representing the syntax of straight-line programs. So that's your take-home message. And so here it is again. We'll replay that, but we won't use monads, we'll use applicative functors. We won't use free monads, we'll use free applicative functors, and you don't see those very often, but they're the go-to tool for the syntactic representation of straight-line programs. And you have to, if you haven't seen this before, you'll have to study it, and you can't study it during the talk, you'll have to study the paper. But maybe it'll give you some intuition. Pear-shaped, if I may say that, pear-shaped free applicative things consist of, for some n, an n-ary function, and not n arguments, but n pairs of arguments. And pair is an applicative functor. And then you're given an n-ary function and n pairs of arguments, you can get a pair of results out of it. And so here again, replaying the structure, I don't need to restrict myself to finitary commands anymore, because I'm not going to be depending on the results of them. I can have infinitary commands again. So I can make applicative programs rather than monadic programs, free applicative programs rather than free monadic programs. And so here are 3 individual commands: the say applicative, the toast applicative, and the sense applicative. And they're just built as using the gadgets for free applicatives. And I can assemble programs, but now I can only assemble straight-line programs. It's only straight-line programs that are accommodated by the free applicative type. So here's a straight-line program that senses and then toasts and then senses, and to fit it on one line, what do I do with the 2 sense values that I get back? I'll just return that pair. So I sense and get a value t, I toast for 3 milliseconds, and I sense and get a value t prime, and I just return the pair t prime. And that's the only kinds of things you can do in this batching. You send a bunch of requests, you get back a bunch of results, and all you can do is then look at the results and return some result that depends, some overall result that depends on the individual results. Here's how the serialization mechanism works. This was the problem with free monads, and serialization works perfectly smoothly for free applicatives. Basically, because it's a straight line program, it's only a sequence of commands that you need to send. So the serialization takes a straight line program and extricates the sequence of commands and makes a sequence of strings and just serializes that sequence of strings. And when you get some stuff back, you have a program that you started with and a sequence of results, and you just kind of pair them up. You zip them up. And that's it. So here's that's my story. The take-home message is that the obvious tool for syntax of programs is the wrong tool for when you want to serialize programs to send across the wire. For this kind of batching process, you want straight line programs, and the right tool for the syntax of straight line programs is not free monads but free applicatives. So this is an advert for free applicatives. And so you get all this delivery mechanism, if you like, for free. So what was in Andy Gill's paper, they built essentially these structures by hand, if you like, and you don't need to build it by hand. You get it for free. The categorical notions are the things that tell you precisely what you need to know in order to build these. An advert for Simon Marlowe's and co-authors' talk this afternoon about the applicative do notation. I think that's what you're going to be talking about, Simon. So this straight line program at the end here is much clunkier than the thing using do notation. And that's because writing programs with applicative functors is much clunkier than writing monadic programs. So come back this afternoon and Simon will show me how to do that better. So I'm going to finish there. Andy Gill's paper inspired me, and my student Matt Pickering I should credit for pointing me in the right direction of free applicatives.
Okay, thank you. So could anyone pass that microphone?
Hi, so I think you've seen the Haxel monad, right?
Sorry?
The Haxel monad.
Yes. I
wonder if you can say something about the difference between what you're doing here and Haxel, and whether any of the techniques you have.
Well, I've seen your talk about the Haxel monad. I wouldn't say I know the details of the Haxel monad, so can I reflect the question back to you?
Well, so in Haxel, there's both a monad and an applicative. And
right.
It's in some ways more flexible because you can interleave applicative things with monadic things.
Yeah, so you don't care so much about straight line programs with these interactions, but when when you do have independence, then you like to be able to batch things together.
Right. So we don't try to send the entire program to a toaster. We would just send batches of commands.
Well, so that might be interesting to explore this. So then if you're wanting to do some latency fixing of a distributed program, you could identify the straight line bits, pack those together. I mean, that's essentially what you're doing, avoiding some round trips in the Haxel interactions, aren't you? So yes, that would be a more sophisticated way of telling this story.
Okay, thanks.
Yes.
Could you go back to the slide with the free applicative monad? I had a question about that. Right. So there in the more option,
yes,
we have a recursive call to free on the function, but the functor is applied to the argument.
Sorry, in more, the instance of for applicative, yes.
Yeah. So what happens if we kind of swap them the other way around? Does that make sense too? Because
so that's why I chose this different way of doing free monads. Where are we? Free monads. So the data type of free monads is the familiar data type of free monads there. And it actually matches the monad class with this definition of the monad class. So if you squint at it, if you take the free m's away, then you get the types that correspond to the monad class. So what's gone on is that you've generalized, well, you've kind of concretized some of the m's to data types, but not all of them. At least one of them has to remain, otherwise you don't depend on m at all. And what's going on with free applicatives is the same thing. So look at the class for applicatives, there's some f's in there. You concretize some of those to free f's, but not all of them, because you need to leave at least one f around. And indeed, there are two ways of doing free applicatives. There's one way you leave this bit as the f, the unconcretized one, and there's another way that's that bit. And there's a nice paper by Capriotti and Capozzi about different ways of doing free applicatives, and they explore the choices between them here.
Okay, yes.
G'day, I'm Hugh. So I maintain optbars at the moment, which was written by Capriotti, but it seems that serialization is similar to the production of the help text.
It seems that I didn't hear the question.
Your serialization across the wire is equivalent to the production of the help text in optbars.
Okay, I don't know that library.
Okay, it just does command line argument parsing. But we had a problem of using the free applicative and the free alternative in that as soon as you go some or many, you essentially get an infinite program.
Right, okay, yes.
So I was just wondering if you had if there's a solution to that apart from the dodgy hack that we do. And
So Yes, I don't know about free alternatives. I haven't thought about that, but in ideal Haskell, where I don't have arbitrary recursion, I've only got inductive structures, then I can only make finite straight line programs. I can't construct in ordinary Haskell, I can of course construct an infinite term that represents an infinite straight line program, but only if I allow myself lazy evaluation and bottoms and things. In idealized Haskell, which you pretend that you're really talking only about total functions and sets, I can only make finite programs, and so I can only send finite things across the wire, which is good because I'm in a hurry for my toast and I don't want to try serializing an infinite program and then waiting for that to get across the wire before I get my breakfast. If that answers your question.
Okay. Okay, the last questions.
So there's a minor cottage industry of more efficient representations of the free monad.
Absolutely.
Do the same things apply to free applicatives?
Yes, they do, and that's kind of one of the discussions in the Capriottian and Capozzi paper. There are kind of left-nested and right-nested ones in particular, and which you want is better. It depends on what application you're doing with it. Yes.
Okay, thank you very much. Thank you, Jeremy.